Then we're gonna have fairly interesting class. I would say it's gonna be a summative of all what we learned up to today. We're gonna use everything that we learned about trigonometry, the acute angle. We're gonna use the sine cosine formulas, basic trigonometric ratios, as well as acute identities. Remember when we could express the formula of double angle through cosine and sine? And I'm gonna show it to you during today's class so you can rewind it, because we're gonna use that today in particular. And we're gonna prove trigonometric identities today. What means trigonometric identity? Basically, equation where left-hand side sets with respect to the right-hand side. So what we're gonna do, we're gonna prove that left side is basically equal to the right side of the equation. On your screen right now, you can see identities based on definitions, reciprocal identities, right? Means if it's based on definition in this case is that this function is reciprocal. Reciprocal is this function raised to the power -1. So reciprocal of sine x gonna be cosecant x. For reciprocal for cosine x is gonna be secant x, and so on. Coefficient identities, Pythagorean identities, which we also covered in previous classes, double angle formulas, and finally addition and subtraction formulas. This is what we covered in the last class. But does anybody remembers this part? Does it rings a bell? So left-hand side is identities based on definitions, and right-hand side identities derived from relationships, right? Because on the right-hand side, we have a relationship between sine, cosine, and their reciprocals, as well as the tangent and cotangent. And on the left-hand side, just identities by the definition. Please take a moment to screenshot this table or just note it down, because it's going to be really useful for your further notice. Let me know once you get a copy of this, whatever way you like. You could write it down or you could screenshot it, because basically what we're going to do next is we're going to try to see patterns in what is written in the formula. It's just like finding the common factor. At some point, you begin just to know the right answer. Same with trigonometric equations. We're just gonna see some dependencies and some patterns, and in order to see them, you gotta be confident with these basic equalities, basic identities. How is it frozen? Oh, I see. Thank you for letting me know, because I've been showing you this for quite a while now. Can you see it this way? I mean, I should be able to do like this and you should see it, no? Okay. Wait. Unfortunately, I cannot play it in a slideshow for some reason. I should stream. Let's do it in easy way. Yeah, here's the identities I've been talking about. Tell me if it's not big enough for you to see it clearly. I would try to enlarge it somehow. I'm sorry for the delay, guys. Here it is. Please make sure to copy down the trigonometric identities in whatever way you like, and let me know if you have a copy of them. Guys, how is it going? Please let me know once you have a copy of this so we can move on. Okay, I see most of you already copied it down. In case if you would need it again, I'll scroll back to this page, okay? And let's start with basic identity. Sine 2x over 1 plus cosine 2x equals tangent x. How do we prove this identity? based on the table that we just had. Now I won't go back. I hope you copied it down. I have it memorized. So let's begin with defining what we have in this equality. First of all, on the left-hand side, we have sine of 2x. Isn't that somehow related to double angle formulas? Well, obviously it is related because we have 2 times x in the angle definition. So it's double angle. So okay, sine 2x we're going to take from double angle formulas. Then 1 plus cosine 2x. Yes, of course, we have cosine 2x here, again, double angle formula. But let's not rush with that. Let's take a look. What else can we find here? On the right-hand side, obviously tangent x, and we know it's basic trigonometric identity that tangent x equals to sine x over cosine x. Let's keep that in mind. See if we can use that later. Okay, 1 plus cosine 2x. Let's see how can we convert cosine 2x, right? Sine 2x, first of all, sine 2x equals to 2 sine x times cosine x. Remember this double angle formula? Well, for cosine 2x, there is another double angle formula. No, it's not even close to sine 2x. It's going to be cosine x, but cosine is squared in this case. Cosine squared of x minus sine squared x. This is first equality, but again, look, there is not much we can simplify here. So we can go even deeper. Cosine squared x minus sine squared x is also equals to 2 cosine squared x minus 1. And look at this. Now, we, instead of having just difference of 2 trigonometric functions, we have 1 trigonometric function, subtract 1. And let's look back at the denominator. I have 2 questions. Yep, sorry, Mohammed texted that he has technical problems. Oh. Let me finish explaining this one, and when Mohammed comes back, he would ask some questions. So cosine squared x subtract 1. And if we substitute it for cosine 2x in our initial formula, look what we're going to get. Sine 2x equals 2 sine x times cosine x. Okay, let's rewrite our initial equation with identity form. Then 1 plus cosine 2x. And if we substitute this part for cosine 2x, right-hand side, we're going to get 2 cosine squared x subtract 1. Is that correct? As soon as we have plus in front of the brackets, no signs are changed inside. And right hand side is tangent x, which equals to sine x over cosine x, right? Next step, let's simplify what we can on the left hand side as well as the right hand side. On the right hand side, there is nothing to simplify. Don't try to factor out x. I've seen examples like that. Don't do that. X is a part of the sine and cosine for functions. So on the left hand side, what can we simplify? First of all, let's subtract 1 minus 1. Now we have only 2 cosine squared x left. What can we factor out now? 2, obviously, another multiple, common multiple in both numerator and denominator. And finally, cosine squared x, and here we have cosine x. So here cosine turns to power 1, and this cosine disappears, getting factored out. Now we can see that in truly left-hand side, sine x over cosine x equals to sine x over cosine x, which is equals to tangent x. Is there any questions, guys? So basically, answer here could be explained as follows. Left hand side equals to right hand side, which proves the identity. Okay, guys, please make sure to copy down this solution. And if you have any questions about my reasoning, please speak up now. Let me know once you finish copying down and we'll move on. Can you hear me, guys? Hello? Okay, great. I got scared for a second. Thank you, Hala. Thank you, Mubashir. Welcome Rana, welcome Mohammed. Please guys, Hala, Hala done, Bashar, Safa. Okay, let's move on. Now clear the drawing. And now we gotta prove that cosine pi over 2 plus x equals negative sine x. This one, does anybody willing to solve it with explanations? That would be really nice. That would be part of your assessment as learning. Anyone? This is the easy one, then it's gonna be harder. Okay, Safa, go on. Can you sketch on the board? Use your pen, draw like me. Safa, you can start. Can you explain while you're writing it? Okay, cosine x equals 1 times sine x. Sorry, Safa, can you explain what exactly you're writing? Because I don't recognize. And which identity do you use for left-hand side? Yeah, but I don't get how exactly they simplify it. Can you what do you do? How this part equals to this part? Mm, you cannot. So it's not. You have to. Let me explain you something here. What you have in the brackets, pi over 2 plus x, it's variable of the cosine function. You cannot just like open brackets here. As I understand, you multiply cosine pi over 2 and plus x, cosine x. So you convert yeah, so basically you try to opening the brackets. Is that correct? Stafa? If I'm right, then you have to understand that what's inside of the brackets cannot be multiplied by x, because cosine x, it's like it's function that depends on what's in the brackets. It's not a operator. We cannot multiply by it. It's not a coefficient. So what you have to do here is to use formula for cosine, for addition and subtraction formulas. Let me move to the first slide. Here on your right hand side, addition and subtraction formulas. You cannot just open brackets because it's not an operation in this case, right? What's inside, you see, basically cosine is a function. Cosine by itself equals to the value in radians. Cosine itself is a ratio on a unit circle between this arm, basically between the base and the terminal arm. And in your case, what's inside the bracket is just the value of this angle. It's not like sum of two different angles. You cannot use it that way. In order to convert what you have inside the brackets as a sum, you have to use the addition and subtraction formulas for sine and cosine. How these formulas are proven, it's another question. For you, it doesn't, some of the basic formulas could be easily proven based on the Pythagorean theorem and basic trigonometric functions. But addition and subtraction formulas are not so easy to prove, and you don't really need to prove them right now, but we can do that by using Pythagorean theorem and more simple formulas. But for now, just use formula as it is. So you see, we have sum, we have cosine pi over 2 plus x. Let's see that addition and subtraction formula. Cosine with plus is right here. So your formula would be cosine x times cosine y minus sine x times sine y. Do you have it? Can you write it down for this case? Basically, what you're going to have is cosine times cosine. First one is x, the other one is y, and then minus sine x and sine y. So Safa, can you continue solving? Yes, you write the addition identity for cosine of sum of angles. You missed something here? Also, meanwhile, I'm going to write an example of when you can multiply by brackets. So in order to multiply cosine by something, no, Safa, sorry for interrupting you, but proper formula would be cosine x times cosine y, subtract sine sine x times sine y. And x and y values are the one in the brackets. In scenario when you would like to multiply by cosine and open the brackets, it should look something like this. For example, cosine x times, and here's the bracket. Here would be, for example, 2 plus 5. Then you can open the brackets in a conventional way. But you don't open in these brackets. That's not what I mean. It's like f of x, you write f of x, function of depends on x. Basically, these brackets, it's not operational brackets. It's brackets that identifying that it's a variable inside of them. F of x, and you multiply f by x, that's not the case. Is it clear now why we cannot multiply like that? Cosine times pi over 2 or cosine x. Guys, is it clear? How, please evaluate this part using values from the brackets. So you're going to have pi over 2 instead of x, right? What it would be equal to? Equals negative sine x. Oh, no, how I don't understand why you, oh, Safa, I'm sorry. Safa, I don't understand why you subtract x from pi over 2. And no, are you using this formula right here? Because if you use it, you only need to substitute pi over 2 for x and x for y. Because this is addition identity for cosine. I just wrote the formula that is on this table. It's right here. I'm gonna use the green color to highlight it. Here, cosine x plus y equals cosine x times cosine y minus sine x times sine y. Okay, this is the formula I wrote. Here, you have for x value, you have pi over 2, and instead of y value, you have x, right? So basically, what you're gonna have is cosine pi over 2 times cosine x minus something. Can you write that? Because we're using addition formula in this case. As you can see in the variable for cosine function, we have pi over 2 plus x. Safa, can you finish this one? Mm-hmm. That's absolutely right. And what is it equal to on the right hand side? It's absolutely right, Safa. Now it's perfect. And remember, at the beginning you said that cosine pi over 2 equals to 0. Now let's use it here to get rid of unwanted terms. Sorry, before going on, write what is the left-hand side equals on the right-hand side. This is important now for us. Wow, this equals to 1, you want to say? But use the given formula, because now we converted cosine pi over 2 plus x into what you wrote here. And we should set an equality with what? We have to prove this identity, that left-hand side equals to the right-hand side. And right-hand side is minus sine x. Left-hand side is cosine of the sum of two angles. And we used addition identity to rewrite it as a difference of product of cosines and product of sines. Yes, Safa, exactly. It would be minus sine x. Then the next line, considering that you previously told that cosine pi over 2 equals to 0, and that's absolutely right, because if you sketch the unit circle, pi over 2 is 90-degree angle, and cosines are arranged on the x-axis. So if it's going to be 90-degree angle, like this, projection of the terminal arm on the x-axis would be equal to 0. Basically because it's perpendicular to the x-axis. So, Safa, would you mind evaluate what you have on left-hand side and simplify it as much as you can in order to prove that it's equals to the right-hand side? Because you're giving with exact value for one of the angles, you can simplify it. Yes, exactly. 0 times cosine x. Yeah. And now, Safa, can you like cross out how do you simplify it in order to prove? Yeah, absolutely right. This part is going to be equal to 0, 1. Basically, we can just bring it in. Yeah, it's going to be negative sine x equals to negative sine x. Great. Is it clear now, Safa, how do we find the identity and how do we prove it? Is it clear why we cannot multiply by cosine like this? Because cosine is function itself. And what is inside the brackets is the variable. It's not like terms here. Okay, great. I'm happy we discovered something new today. So if anybody needs more time to copy this down, please let me know. here I would mention that this is equals to cosine x plus y. In our case, y equals to pi over 2. Oh, sorry, y equals to x, and x equals to pi over 2. That might be a little confusing, so let me mark them as x1 and y1. So x1 and y1. So it's not confusing that we have y equals to x and x equals to something else. Guys, I believe I gave you enough time. I'm just gonna clear the board and move on to the next one. Here it's two identities for sum and difference of two angles, addition and subtraction identity. On the right hand side, let's see if we have something like that on the first slide that we had today. 1 plus tangent x times tangent y. For now, I'm not sure if there is something that could be used for this identity. Let's start with opening cosine x minus y and cosine x plus y. But before that, I suggest we make a 10 minutes break because it's already 45 minutes into the class. Let's make a 10 minutes break and then we get back to next problem. I'm going to show you how to solve this one. Okay, guys, I'm back. Is everybody else back too? Okay, guys, let's get to the solution of this example. And again, we're going to begin with what we know for sure. Cosine x minus y over cosine x plus y. We know addition and subtraction formulas for cosine and sine function. For cosine x minus y, formula is going to be as follows. Cosine x times cosine y plus sine x times sine y. And this, you see, only thing is different between plus and minus is the sign between the terms. For minus, the subtraction formula, when the difference of two angles, we have plus here, and for sum of two angles, we have minus there. So our final expression would look as follows. Basically this part over exactly the same part, but sign would be different. In the denominator, we're going to have minus here. Minus sine x times sine y. Is that clear? Now this part equals to 1 plus tangent x times tangent y over 1 minus tangent x times tangent y. And what we see here, that up until now, it's not really clear how can we factor something out here. Is that correct? Any ideas, guys? What would be the next step? I believe, guys, nobody has an idea what to do next. And I'm gonna tell you that now let's write the identity for the right-hand side, right? Left-hand side we already expanded. Is that correct? This is cosine x minus y over cosine x plus y. Now let's work on the right-hand side. On the right-hand side, what do we have? We have 1 plus tangent x times tangent y, and 1 minus tangent x times tangent y, which would be equal to the following. 1 plus tangent x. What is tangent x? Is the sine x over cosine x. Don't forget about basic identities. Definition of tangent, sine x over cosine x. Then times sine y over cosine y, right? Now denominator. We have 1 minus sine x over cosine x times sine y over cosine y. Make sure to copy down with me. So now, the next step, we have to, basically here we have product on denominator and numerator, right? So we can join these two together. I have sine x times sine y over cosine x times cosine y. Plus 1 plus. So how do we add 1 to any of these terms? We have to bring it to common denominator, or multiply 1 on top by cosine x times cosine y, both numerator and denominator, and on the bottom multiply by the same multiple. What we're gonna get as a result? We're gonna get cosine x times cosine y on the same denominator plus sine x times sine y divided by cosine x times cosine y all together over, this is our numerator, right? All together, and our denominator would be cosine x times cosine y, 1 times this common denominator minus sine x times sine y, and again denominator is cosine x times cosine y. And what we can see, that basically our numerator is a fracture and our denominator is a fracture. So what we're gonna do, when we divide by a fracture, we flip it over. Now we're gonna have a product. Let me clean the first part. I hope everybody copied that down. I'll move this up a little bit. And now, next line, it is equal to cosine x over cosine y plus sine x times sine y over cosine x times cosine y times cosine x times cosine y in numerator over what was in the denominator before, now in the numerator, cosine x times cosine y minus sine x times sine y. And now by multiplying, we can cross out these two terms because they're equal and both are located in numerator and the other one is denominator. And left behind is what is in the brackets, right? And in the brackets, we have exactly here in green color, this is our cosine of x minus y function, right? Look, cosine x times cosine y plus sine x times sine y. You see the sign is opposite. Then here in denominator, we have cosine x plus times cosine y minus sine x times sine y. So this is cosine x plus y, and which would be equal to initial identity. You see left-hand side here is cosine x minus y over cosine x plus y, and right-hand side we just showed that it is equivalent to what is on the left-hand side. Is it clear, guys, how we solve this one? Basically, usually you have to unfold as much as you can. So here we could unfold it sum and difference formulas, and on the right-hand side we could unfold tangent formula. Take a moment to copy this down, please. Let me know once you're done. Thanks, Safas. Thank you, Hala. Anybody else? Done copying this down. This one is one of the most important ones because here you saw that not only what left or right hand side should be expanded, both sides could be expanded. Anybody else, guys? You finished? Muhammad? Anybody else? Mo? Okay, thank you. I see most of you finished. Then let's move on. Looking at the next one, we have to prove that tangent of 2x minus 2 tangent 2x times sine squared x equals sine of 2x. Here I can identify several identities. First of all, tangent, then tangent of 2x again here. Sine of 2x, these are all double angle identities. Okay, what else do we have in here? Sine squared x, not really an identity by itself, but is part of other identities. So let's start by opening tangent of 2x. Yeah, okay, so tangent of 2x equals to 2 tangent x over 1 minus tangent square x. Is that correct? Anybody else has identities by them? You can trust me that tangent of double angle equals to 2 tangent x over 1 minus tangent square x. And we can see, using that, we can rewrite the following identity as 2 tangent x over 1 minus tangent squared x minus 2 times tangent 2x again times 2 tangent x over 1 minus tangent squared x times sine squared x equals to sine 2x. And what is the double angle for sine function? For sine function, it would be 2 sine x times cosine x. Great. First of all, let's see on what we have here. On the left-hand side, we have common factor of 2 tangent x here and there. Common denominator, obviously. So basically, we could bring it in to the one, basically same fraction. It would be 2 tangent x, bracket opens. This our factor that we bring out, 2 tangent x equal, and in the brackets left we have 1 minus 2 over, because here we have multiple of 2. Oh, and not just 2, it's also going to have 1 minus 2 sine squared x, right? Another multiple that we have here. Now bracket closes, and now denominator is going to be 1 minus tangent square x. Okay. So what can we conclude here? That in the brackets 1 minus 2 sine x, is that any type of identity? One minus 2 sine squared x. Anyone? Is there any way we can convert this identity one more time? Okay, here actually are two identities are hidden. First one, I'm gonna use the red color, is 1 minus 2 sine 2x. 1 minus 2 sine squared x. This identity is related to double angle for cosine 2x. Cosine 2x equals to 1 minus 2 sine squared x. And another identity is tangent 2 tangent x over 1 minus tangent squared x. That's also an identity, but for formula of double angle of tangent. Tangent to x this equals to. You see, now we can basically we expanded, we unfolded the initial double angle for tangent. And what we see now that there was double angle for tangent and cosine squared x. Well, next step would be to show that it's basically equals to tangent 2x times cosine 2x, which equals to initial formula as sine 2x, or in other words, 2 sine x times cosine x. But tangent 2x equals to sine of 2x over cosine 2x, isn't it? This is a basic trigonometric identity for tangent. Tangent equals to the ratio between sine and cosine of a tangent angle. So sine of 2x over cosine 2x times cosine 2x, you see? And how luckily cosine 2x is being factored out, basically simplified in this equation. And what we get as a result, sine of 2x, you can also expand it or just say that the right-hand side, as we showed it, equals to the left-hand side. Right now, I would like to tell you guys that you could have done it even easier before opening all of these brackets, but you would have to see it. How? If you look at the initial equation, if you look here, I'm gonna use yellow pen. If you look here, we could have factored tangent of 2x right away. And if we would do that, what would we get? We would get tangent 2x times 1 minus 2 sine squared x. And here you can see it right away that 1 minus 2 sine squared x should be equal to cosine of double angle, and you factor it with tangent of double angle without this first step of unwrapping it. But it's only under condition if you noticed it. Is it clear, guys, my reasoning about how do we prove identity in this scenario? Guys, any questions on this one? Because this, I would say, was not the hardest one, but not the easiest to get. Guys, if no questions, I'm clearing the desk now. No questions? Okay, guys, I treat it as there is no question. Thank you, Hala. And now, give me a second. We're gonna touch a little bit of the next class, just so you get an idea. So here it is. First of all, I would like to congratulate you with covering Unit 4. And now, take a glance on the next unit, what we're going to start with. We're going to start with graphs of trigonometric functions. For this particular exercise, you are asked to complete the coordinate axis for sine function over the whole domain from 0 degrees to 360 degrees. Let's do this one together. This one is in radians, and the other graph is in degrees. Let's start with radians, and I think we'll see how we go from there if we have more time. So first of all, here's all the x values in degrees, as well as all the x-axis in radians, with the step of pi over 4, or 45 degrees. Remember, pi over 4 is 45 degrees. You can also see it in the table. We have to evaluate value of the y for sine x, basically value of the function sine x at the given radians. For sine x pi over 4, do you remember? Based on the basic trigonometry, basic triangles, triangle with 45-degree angles, right? Has 2 equal sides, and hypotenuse equals the square root of 2. So sine of an angle of 45 degree, or sine of pi over 4, would be equal to 1 over square root of 2. So 1 over square root of 2. 90 degrees. Remember, how can you identify 90 degrees? From the unit circle. 90 degrees angle is basically parallel to the y-axis, right? And y-axis represents the projection of sine. And sine here would be equal to 1. So pi over 2, sine equals to 1, maximum value of a sine function. Then 135 degrees, which is in second quadrant. And here it's best to remember the CAST rule, C-A-S-T, which says that in second quadrant, the only function that is positive is the sine function. So sine function of pi over 3 pi over 4, basically, remember, how do we convert it? We say that sine equals, sine of 3 pi over 4 equals to cosine of pi minus 3 pi over 4, which is equals to cosine of pi over 4, right? Which is equal to 1 over square root of 2. And you can double check it in the second quadrant. Basically, this angle is 45 degrees, right? So it's in the same position as the 45-degree angle in the first quadrant. For sine, even the value is the same. Projection on the y-axis is in the same point. And for cosine of 45 degrees, like this, projection is also 1 over square root of 2. So for 135 degrees, we write 1 over square root of 2. Here's 1, here's 1 over square root of 2. Then for 180 degrees, what is it? For pi value, this is the open angle, like this, 180 degrees, pi value is here. And for sine value in this case, perpendicular projection, vertical projection is basically, is going to be 0, equals to 0. So sine of pi, sine of 180 degrees is 0. And finally, sine of 5 pi over 4. is in fourth quadrant, and here it's negative again. Sine value in the fourth, or sorry, in third and fourth quadrant is negative. So again, projection would be the same by modula as for the 45-degree, but opposite in the sign. So it's going to be -1 over square root of 2. You can prove it again using the cosine. Okay. What you're going to see. That next angle is 270 degrees, is 3 pi over 2. 270 degrees. You remember it's straight down. This is 3 pi over 2. 270 degrees. In this position, sine value equals to its maximum, minimum value, -1. Then again, 7 pi over 4 would be again negative, because in the fourth quadrant only cosine is positive. It's going to be -1 over square root of 2. And at 2 pi, finally, again, it would equal to 1. Oh, to 0, sorry. And if we were to sketch this graph, let's plot all of these points. Let's start with pi over 4. It's going to be 1 over square root of 2. It's somewhere 1 divided by square root of 2 is somehow less than 1. I would say it would be somewhere here. And to be exact, let's use the calculator. So square root of 2. Square root of 2 is 1.41, and 1 divided by 1.41 is 0.7. Yeah, so I'm somewhere close. It would be somewhere here. This is 1 over square root of 2. This is first point, then pi over 2, it equals to 1. Then again, 3 pi over 4, it's again 1 over square root of 2. Then in pi, it equals to 0. Then in 5 pi over 4, it equals to -1 over 2, 1 over square root of 2, but negative, so now downwards. 3 pi over 2. Oh, sorry, 5 pi over 2 here. And the next point would be 3 pi over 2 is -1, minimum value. Next one, 7 pi over 4. Again, -1 over square root of 2. And next one, 2 pi is 0 again. And you may see already how all of these dots. Oh, we forgot about 0 degrees. And what is the value for sine function when x equals 0? Any ideas? When the angle is 0, can anybody answer this question? Last one. I basically give you answer to all of them. And final question is, what sine of 0 degrees is equal to? Anyone? Make a guess, guys. Guys, please, any suggestions? Okay, if I were you, I would use the unit circle and see that 0-degree angle is equal to 2 pi, basically. And for 2 pi, I identified that sine of this function equals to 0. Thank you, Safa. So it would be 0 at the beginning of the coordinate axis, then another point here, 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 and then going to negative values, going back to 0, and after, if you keep adding by pi over 4, for example, next step would be 9 pi over 4, right? 2 pi is 8 pi over 4, plus pi over 4 is 9 pi over 4. So basically, you would start going back to positive values like this. And this is the coolest thing about sine and cosine function, is that they are periodic. They turn back to their previous values after making a complete cycle of 2 pi. Basically, after this, sine wave would repeat itself. Look, we can move this here, and we gotta get the right graph. You see? And we could also move it to the left and get the right graph as well. You see? This is the graph for the sine function in radians. Cosine would be offset by pi over, by pi over 2. It would look like this. You see, with the shift of pi over 2. Yep. So this shift, and also cosine is going to be flipped other ways. Let me show you. Not like this, but when x equals 0, cosine actually equals to 1. So it's going to start like this. You see? And what I wanted to show you that this difference between maximum values for cosine, this is sine function, sine x, and this is cosine x. And difference between their phases equals to pi over 2. And you can see it on this graph as well. From 0 to pi over 2, they're basically offset. Basically, what else can you tell? That sine of pi over 2 equals to cosine of 0 degrees. And between every point, you're going to have this offset of pi over 2. For example, sine pi equals cosine of pi over 2. Basically, what conclusion can we make from here? Also, that sine x equals cosine of x minus pi over 2. Okay, guys, I'm gonna clear this now. And I would love you to do exactly the same thing, but with degrees, while we still have a little more time, so you can practice sketching the sine function. Also, it is preferable to fill out the tables of characteristics. Or you know what, to make it more interesting, let's keep degree for homework, and now just start doing the cosine for radians. Set the values in the table to begin with, and at home you can start sketching the cosine function. If you have any questions, right now is the best moment to ask them, because class finishes soon, and it would be nice if we can go through what we covered today. I think that's exactly what we're gonna do now. Once you fill out the table, okay? Okay, guys. Oh, marks for the test, you mean? Safa. Mm, for everything? I believe I marked most of your assignments. I'm gonna check it. Yeah, I believe I'm graded most. If there are some new assignments, I'm gonna look up into them, but your Safa, I remember I graded most of them. No, before the midterm marks, I marked all of them. Okay, I'm gonna look into that. Now let's quickly review what we covered in today's class. Oh, yeah. Um, I'm not sure for how long I've been muted. I was just reviewing what types of identities we used. And also I reminded you that it is very important to remember these identities by heart because most of them are super easy. You basically have 3 identities in each block, right? For addition and subtraction formula, only difference in them is the sign. Coefficient and reciprocal identities are coming from the definition of basic trigonometric function. So the thing that you have to remember is Pythagorean identities, double angle formulas, and addition and subtraction formulas. And the time of the class came to an end. Thank you everyone for attending. If you have any questions, feel free to email me, and thank you, Safa, for clarifying about marks. I'm gonna look into them later today. Okay? And make sure to start preparing for a test based on this past 5 classes for unit number 4 that we covered within this and the last week. And yeah, you're free to go now. If you have any questions, feel free to ask. I'm gonna wait a few more minutes